Hello friends, today we will solve the digital electronics problem of electronics and communication paper of GATE 2025. Okay. So this is the first question. Here it is said that 3 input majority logic gate has input XYZ. The output F of the gate is logic 1 if 2 or more input is 1 and output is 0 if 2 or more input is 0. So this is typical 3 input majority gate. So which of the following is Boolean expression of the output F? So for such questions, easiest way is to make the table of all four options. Okay, and I just check them. So usually I start with middle values. So for example, when we take x, y, z, so this is 0 1 1 suppose. So when we multiply these three, then we get 0. So this cannot be true because there are two ones, so output should be 1, but here it is 0, so this thing cannot be true. Similarly, if we take x plus y plus z for this value, then 0 plus 1 plus 0 is 1, but here zeros are more south, so this cannot be majority gate. Similarly, if we see this part, then here x is 0, okay, and 0 XOR 1 XOR 0, 1 XOR 0 is 1 and 0 XOR 1 is again 1. So it is giving output 1 although number of zeros is more. So this cannot also be true. So but if we check this part, then this is like 0 plus 0 plus 0. So here also it is satisfying, here also it will satisfy all four, all the 8 options. So correct answer is A. Okay. So by this method, you do not need to use any boolean algebra or anything, and just you can get to the answer quickly without using anybody. Okay. Second question is like on full adder circuit, and then there is an XOR gate also here. So here it is input X, here it is Y XOR, and Z is always equal to 1. Input Z is connected to the carry in input, and this is 1 also as carry in. So if input Z is logic 1 पे set as, and the circuit will function as. So basically you can see that the output F is equal to X, okay, plus Y XOR 1. So Y XOR 1 is Y bar, because Y it will is equal to Y bar 1 plus Y 1 bar. So this part is 0, so this is Y bar. So this part is Y bar, this part is X, and this part is 1. So F is X plus Y bar plus 1. Now Y bar is basically can be treated as 1's complement of Y, okay, and 1's complement of Y plus 1 is 2's complement of Y. So this is basically X plus 2's complement of Y. Okay. Now in number system we learned that to subtract two unsigned numbers X and Y, what we usually do is we use X plus 2's complement of Y. Okay, we take 2's complement of Y and then we add them, so this will give us X minus Y. So that's the way to subtract two unsigned numbers, okay, using 2's complement. So here also this funda is working. X plus 2's complement of Y can be treated as X minus Y. So basically this thing will work as subtractor. Okay, so B is the correct answer. Now we come to third question, which is on a digital to analog converter. Okay, so it is a 4-bit DAC with input B3 B1, B3 B2 B1 B0, MSB to LSB. So this part is MSB, this part is LSB, and it is designed using ideal op-amps, which is closed when the corresponding input bit are logic 1. So if it is closed, it means the bit is logic 1. Now the question is, when the input B3 B2 B1 changes from 1110 to 1101, the magnitude of change in output voltage V0 जो कितना होगा? So you can see that input is changing from 1110. So 1110 is basically 14. Okay, it is 8 plus 4 plus 2 plus 0, so it is 14, and from 14 it is changing to 1101, which is 13. Okay, so 14 to 13 change is basically the output is changing by just 1 unit, which is which is 1 resolution. Okay, so by 1 step size is like 1 resolution. Okay, so we just need to find the change in input is equal to 1 resolution, and we know that to find the resolution of any DAC we just need to give the input as 0 0 0 1. Okay, just keep b0 the lsb bit as 1 and make all other bit as 0, and then we will get the resolution of any DXV. So here also we will do this. So we will make this thing 0 0 0. So we will keep this switch open and we will only keep this thing 1. So basically this circuit will simplify to 2 volt, 8R, and then this R, and then this thing. So basically this will simplify to a simple op-amp, ideal op-amp problem. Okay, so this current is equal to this current, so 2 minus 0 upon 8R is equal to, because this current is 0, so this will have to go to this part only. So this is 0 minus V naught upon R. Okay, so 2 by 8R is equal to minus V naught upon R. R cancels, so it is 1 by 4 is equal to minus V naught, so V naught is minus 0.25. We need to find the answer in millivolts, so V naught, magnitude of V naught will be 250 millivolt. Okay, so answer to this question is 250 millivolt. Fourth question is on ADC. It's a 10-bit A to D converter, has sampling frequency 1 megahertz and full scale voltage as 3.3 volts. So for the input sinusoidal signal with frequency 500 kilohertz, the maximum signal to noise ratio in dB and data rate in Mbps at the output of the ADC is. So here we can use basic formula. The data rate in Mbps of ADC is n into fs. So n is the number of bits, so it is a 10-bit ADC, so n is 10 times the sampling frequency, okay, of the ADC, which is 1 megahertz. So this is basically 10, and then hertz is per second, and this is mega, so 10 megabits per second. 10 Mbps is the data rate of this ADC. Okay, second thing we need to find out is signal to noise ratio in dB. So for a general ADC, it is 1.76 plus 6.02 times n is number of bits, so simply just putting it, we get 61.96 dB. Okay, so 61.96 and 10 is the correct answer. Okay. Next question is on sequential circuit part. It is a tricky question. It is saying that a positive edge triggered sequential circuit is shown below. There are no timing violations. Input P0 is set to logic 0. So this part is set to logic 0 always. P0, and this is set to logic 0 at all time, and P1 is set to logic 1. So this part is set to logic 1 at all time. Okay, so the timing diagram of select and as this and this thing, a timing diagram is given. So the sequence of output y from time t0 to t3, we need to find the sequence of output y. Okay, so output y is basically q0 bar XOR q, let's say this is flip flop 0, this is flip flop 1, so this is q0 bar XOR q1n, which is also equal to q0n XOR q1n. Okay, because when this thing will change, then immediately this thing will also change. Okay, because there is no delay in this part. So basically output is p0n plus XOR q1n. So this is the expression for the output y, and now we need to see the values of select and s at different time and find out. So just before the first clock come, you can see the value of select is 0 and s is 0. So select is 0 means this 0 will come here. Okay, and this select is 0, so this select is 0, so this one will come here. Okay, initially. Now at the first clock edge, what will happen, this will sample these two value, and D flip flop, we know that next output is present input, so this 0 1 will after first clock edge will pass to output as 0 1. Okay, so the output after first clock will be 0 1. Then at second clock we can see select is 1 just before second clock edge, positive edge, and select is 1 and s is 0. So select is 1 and s is 0, so this part is 0, so this will come here. Okay, and this is select is 1, so this previous thing bit will come here, so previous bit was 0, so 0 will come here. So just before second clock edge the input was 0 0, so after the second clock edge the output will be 0 0. Okay, so this is the after second clock situation, after second clock. Then at third clock edge, just before third clock edge, this is 1, this is 1. Okay, both are select and S are 1, so this select is 1 and this is 1, so this 1 will come here. Okay, the select is 1, so this previous bit will come, so previous bit was 0, so 0 will come. Okay, so input was 1 0, and just at the clock edge, this after the clock edge, this 1 0 will transfer as output 1 0. So after third clock edge, output of both flip flop will be 1 0. Okay, and after fourth clock, just before fourth clock, select is 0 and S is 1, so select is 0, so this part will come here, and select is 0, so this previous thing will come here. Okay, so this part is 0 and this part is 1, so after the fourth clock what will happen, this 0 1 will transfer to output, so the output will be 0 1. Okay, so we know the output of both the flip flop after all 4 clock pulses, so therefore this is like 0 1, then it is 0 0, then 1 0, and then 0 1. Okay, so we'll simply XOR them, so because we just need to XOR them, so this is 0 XOR 1 is 1, then 0 XOR 0 is 0, then 1 XOR 0 is 1, and 0 XOR 1 is 1. So basically the sequence will be 1 0 1 and 1, so this is the correct answer. Okay, so A is correct answer. Last question is on timing problem. Okay, so it is saying that in a circuit shown below, the AND gate has a propagation delay of 1 nanosecond. The edge triggered flip-flop has setup time of 2 nanoseconds. So setup time is 2 nanosecond, and AND gate has delay 1 nanosecond. Hold time is 0 nanosecond, and clock to Q delay, which basically means clock to Q delay or propagation delay of both the flip-flop is 2 nanosecond. So the maximum clock frequency such that there is no setup violation is. Okay, so here what we can see is that we need to apply this timing equation in two cases. First, from input of flip-flop 1 to input of flip-flop 2, and then in second case we need to apply this from input of flip-flop 1 all the way to input of flip-flop 2 to input of flip-flop 1. Okay, and then see which one is giving me the minimum clock frequency. Okay, so for first case we need to apply it. So the equation we will use is T clock should be greater than T setup plus T propagation delay plus T propagation delay of combinational circuit. So for input of flip-flop 1 to input of flip-flop 2, we will use T clock 1 should be greater than equal to T setup of flip-flop 1, पहले वाली चीज, then propagation delay of flip-flop बीच वाली चीज, and then combinational circuit from 1 to 2 if there is any combinational circuit between 1 and 2. So T clock 1 should be greater than 2 nanosecond. Okay, then this part propagation delay 0 and propagation delay of flip-flop 1, so this is 2 nanoseconds. So T clock 1 should be greater than 4 nanosecond. Okay, in case 1, which basically means F clock 1, which is equal to 1 upon T clock 1, is equal to 250 megahertz. Okay, and in second case T clock 2 should be greater than equal to setup time of flip-flop 2 plus propagation time of flip-flop 2 propagation delay, and then the combinational circuit connected from 2 to 1. Okay, so this part is 2 nanosecond, propagation delay of flip-flop 2 is 2 nanosecond, and propagation delay of combinational circuit is 1 nanosecond. So this time T clock 2 is getting more than should be greater than equal to 5 nanosecond. So F clock 2, which is 1 upon T clock 2, is 1 upon 5 nanosecond, is 200 megahertz. Okay, So it should be like maximum 200 megahertz. This is like maximum 250 megahertz. So we always choose the minimum frequency so that this will also work and this will also work. Okay, so we need to choose the maximum clock frequency. So f clock net maximum is equal to 200 megahertz. So these were the 5 questions on 6 questions on digital electronics. Thank you.